So in this video we're going to be talking about metric spaces and open balls. So I'm just going to define what a metric space is, and this may seem like a pretty vacuous definition given what we've already covered, but just want to make sure there's no ambiguity when I talk about a metric space. So a metric space is just a pair consisting of a set X and a metric D, which is defined on X. And you may be thinking, well, I already know this, but I just want to make absolutely sure that when I talk about a metric space, you understand that I'm talking about a set and a distance function, or a metric defined on that set. So X is a set and D is a metric. So now that we have a good grounded concept of distance, then we want to start kind of thinking about, well, what are the things which we use distance for? And one of the things we use distance for is in things like radiuses, right? If we take the plane and we want say a point, and we want to consider, say, all the points which are in a certain radius around this point, then we use our normal Euclidean metric, like so we make a circle around this point, and these are all the points which are within say, let's call it our distance of that point. So what happens when we try to apply this concept to other sets with other metrics? Well, hopefully you can kind of see what we're trying to do. We're trying to find the set of all points. If we take a point, we're trying to find the set of all points which are within a certain distance of that point, given the particular metric which we're using for that set. And so I'm going to introduce now the concept of an open ball. And you can see this as a ball in 3 dimensions. It would be a sphere if you wanted to, in 3-dimensional space, if you wanted to take all the points within a certain distance of a particular point in 3-dimensional space, you'd get a sphere. So the open ball, let's call this B for ball, of radius r, so this is the radius, around a certain point C. Okay, so this is a ball of radius r around a certain point C, where C is in our set. So C is in X. And so this ball of radius r is exactly how I described it. It's going to be the set of points X in X, which are at most r distance, well, less than r distance from C. So these are all the points X which are within r distance of our point C, and that's should be pretty intuitive concept, right? It's a ball of radius r around a point C. So this is an open ball. Open ball. And this idea of openness is important, but this we'll discuss more in depth in the next video. But just for now, just accept that this is an open ball, and there's some significance to it being open. You might be able to see already that this is less than r. So this diagram is a little bit misleading. It should really be sort of a dotted line around a point, because we're not actually including the boundary of this circle, because it's less than the radius. So we're just including the points which are up to the boundary, but not actually including the boundary. So this is why it's quote unquote open. So what, for example, would be an open ball in, say, the discrete metric? If we take just a set, I'll just draw this out before I do the math. So just some set, and remember the discrete metric, the distance between any 2 points is equal to 1. So what is a ball of radius r around a point? Well, if say r is less than or equal to 1, and a ball of radius r around a point C, let's call this point C, by definition is all the points which have distance from C less than r. So less than 1 distance away from C. Well, all the points have distance 1 from C. Every point has 1 unit of distance from C. So the set of points, the subset of points which are less than 1 unit of distance away from C, is just C. You know, it's these. There's no point has less than one distance away from C. So, but what if R is greater than 1? What if R is greater than 1? Then say for example R is 2. Just pick a number. Say R is 2. Then what are the points? How many points are there that are less than 2 units of distance away from C? Well, all of them. Everything has distance 1 from C, so the set of points which have less than radius 2 units away from C is every point. So every point is in this ball. So we can rewrite this explicitly as so the ball, this is for the discrete metric. The ball of radius r around C is equal to a piecewise function. So it's equal to just the set C if r is less than or equal to 1, because there'll just be no other point in it other than C. And it will be the entire set, so it will be the entire set X if r is greater than 1, because every point will be in the ball of radius anything greater than 1. So let's do another example. Let's say we have the max metric on R2. So in R squared, in the max metric, I'll just draw out the plane, and suppose we have a point. Then what points are our distance away from this point C in the max metric? Well, remember the max metric is the distance is defined by the largest difference in any one single component. So say this is distance r from C in one direction, and this is distance r from C in another direction, in the second coordinate, and this is also distance r from C, and this is also distance r from C. So the ball is going to be everything that is less than r distance in any one direction. So this is these points. So this ball is in fact a square. And so this ball in the max metric is going to be the set of all points. So the ball of radius r around C is going to be the set of all points x in x. So these have coordinates x1, x2, and C has coordinates c1, c2. The set of all points x in x such that x1 minus c1 is less than r. This is in the first direction. The absolute value of x1 minus c1 is less than r in any direction. It never exceeds this. And x2 minus c2 distance is less than r. And so in the next video we'll be talking more about the idea of openness and open sets, not just open balls.